Good day, everyone. Welcome back to another lecture in the series Organic Chemistry 1. So, this is lecture 2, and we will be talking about acids and bases as well as reaction mechanisms. So, the first question I want to ask today is why acid base in organic chemistry? We all know about our acids and our bases, or hydrogen chloride or hydrochloric acid. We know about our sulfuric acid and all of these mineral acids and bases. So why acid-base chemistry in organic chemistry? So, understanding acid and base chemistry will lead to a better understanding of organic chemistry. Once we can apply these acid base principles to reactions, it helps us to understand and to be able to predict the product of a reaction rather than trying to memorize the whole thing. Now, firstly, we must set the stage for acid base. What are the definitions? So we're going to look at two. The first is Bronsted-Lowry acids and bases. And for this definition, it's defined as reactions which involve the transfer of protons. So therefore, a Bronsted-Lowry acid can donate or lose a proton, and a Bronsted-Lowry base can accept or remove a proton. So we have an example here. We have hydrochloric acid and we have water acting as a base here, and the product of that is our conjugate acid and or conjugate base. So according to Bronsted-Lowry, HCl is an acid because it loses a proton, right? So we have our HCl here and it loses or liberates a proton, and that is why it is considered a Bronsted-Lowry acid. For the base and water in this case, it can accept or remove a proton, right? So here clearly we have water, and the hydrogen that was liberated from the acid now protonates the base. And since the base accepts a proton, it is considered to be a Bronsted-Lowry base. The other definition that we're looking at is Lewis acids and bases. So this definition, or if we go into the definition of Lewis acids and bases, it's a little bit different, but underneath it's basically the same principle. So Lewis acids are electron pair acceptors, and Lewis bases are electron pair donors. Therefore, proton donors are not the only acids. And I think that's the key point here for Lewis acids and bases. So you will have acids and bases that are not proton donors according to what we just defined from Bronsted-Lowry. So any electron deficient atom can act as a Lewis acid. So we have two species here. We have aluminum chloride, which is acting as our Lewis acid, and it is considered to be a Lewis acid. Why? Because it can accept a pair of electrons, as is demonstrated by our arrow. And again, just to reinforce our arrow movement and what it means, wherever the arrow starts from is where the bond is broken. So this CCl bond is broken, and this is a new bond that is formed between the chlorine and the aluminum. So the chlorine donates a pair of electrons to aluminum, right? So this is a little bit different from our Bronsted-Lowry acids and bases, where we're looking specifically at proton donors or acceptors. And Lewis acid, Lewis says, it's not just about proton. Whether a species can accept or donate a pair of electrons, we can classify them as acids and bases. All right, so the aluminium atom only has a sextet of valence electrons. Therefore, it can accept an electron pair without breaking any bonds. So if this is the Lewis structure of aluminium chloride, and as we know, one line represents a pair of electrons. So if we count 2, 4, 6, that basically accounts for our sextet of valence electrons, and therefore aluminium is able to accept another pair of electrons without breaking any of the aluminium chloride bonds. A key point here also is that all Lewis acids are electrophiles, and if we recall from the previous lecture, we should know what that means. And all Lewis bases are nucleophiles. So just to give some examples of Lewis acids and bases, so we have met aluminium chloride already, but there are some other species. So I mean, here we're looking at water being a Lewis base, ammonia, other amines, um, alcohols being Lewis bases. And then for the Lewis acids, we see other species apart from aluminium chloride, other aluminium compounds, and of course, boron is a similar compound to aluminium because it's able to accept another pair of electrons as well, and therefore would be a very good Lewis acid. All right, so our first question is identify the following. So look at the reaction and tell me what is the base, what is the, Lewis, both Lewis acid base, Bronsted-Lowry acid base, and electrophile and nucleophile. So based on the knowledge that we have just gained, or that you had previously, pause the video, answer this question before we go into the answer. All right, so if you had that this species is the Lewis acid, it is also the electrophile, and it's also the Bronsted acid. And if you had water as the Lewis base, as the nucleophile, and as the Bronsted base, then you would have had it correct. So our follow-up question, which is what I expect to get the answer for in our upcoming lecture. So our follow-up question 1 is A, distinguish between Bronsted-Lowry and Lewis acid. That's A. And B, why are all Lewis bases nucleophiles? So answer those questions. All right, so now we're going to go into a little bit into acids and bases in organic chemistry. So as we know, most acids and bases that have carbon atoms in the structure are actually insoluble or only sparingly soluble in water, right? So we usually use other solvents to dissolve these organic compounds. So solvents such as diethyl ether or dichloromethane, we use to dissolve these organic acids or bases. And most strong mineral acids that we're familiar with are insoluble in organic solvents, and so a mixture of water and an organic solvent is used. So now we're going to talk a little bit about acids and bases in organic chemistry. So let's look at these reactions, and just note that the length of the arrow gives an indication of where the reaction is going mostly, right? So this long arrow here indicates that, in the presence of water and HCl, hydrochloric acid, we have formation of hydronium ion primarily, right? So let's look at the arrow to see the direction of the reactions generally. All right, so for formic acid here, right, in the presence of water, we can formate anion, right, and the hydronium ion. However, notice the length of the arrow, which suggests that the reaction generally goes in the opposite direction. So we have very small formation of the formate anion, which suggests that, it's a weak acid. And of course, we have ethanol here with water, and in the presence of water, it can form an ethoxide anion. However, based on the direction of the arrow and the length of the arrow, it suggests that the reaction is normally going in the opposite direction. So since formic acid is a weaker acid than HCl, the equilibrium lies more to the left when compared to the reaction of HCl, as we said before. So continuing our acids and bases in organic chemistry, if we compare that with organic solvents, right? So we have the same formic acid in diethyl ether, and the reaction is more to the left in this case as well. Very few formate anions and very few protonation of our diethyl ether. However, in the presence of acid, or ethanol is protonated, right? So the formic acid does not ionize as much in ether as it does in water. Therefore, water promotes ionization to a greater extent than ether, right? Which should make sense. And the formic acid, therefore, is a weaker acid in ether than in water. And so clearly the strength of the acid depends on the base it reacts with. So how can we determine the strength of an acid, right? So this equation should be familiar to you guys. So we have our equilibrium constant, which is equal to the product of the products, which, the acetate and the hydronium ion, the concentration of these products divided by the concentration of our acetic acid. So at 25 degrees Celsius, the acidity constant for acetic acid is 1.76 times 10 to the minus 5. And once we calculate the Ka, we can therefore take the minus log of it to calculate the pKa. And something to remember is that the greater the pKa, the weaker the acid, which is similar to our pH, right? So numerically speaking, with our pH, the higher the pH, so for example, if we're comparing a pH 6 acid to a pH 1 acid, we know that a pH 6 acid is weaker than a pH 1 acid, right? So similarly, the greater the pKa value, the weaker the acid. So just to note here as well, for strength of bases, similarly, the stronger the acid, the weaker the conjugate base, right? And the larger the pKa of the conjugate acid, the stronger is the base. And you might want to repeat that and visualize it in order to get it, right? So we have these two diagrams here, and one represents acid and the other bases, and we have the Ka values here. And so as we can see here, going all the way from the hydronium ion to water would be a very weak acid with a Ka of 10 to the minus 14, while the hydronium ion will be a very strong acid with a Ka of 1. And for the bases, water, again being amphoteric, it can be basic as well as acidic, right? So it is a weak base with a Kb, in this case, of 10 to the minus 14, while the hydroxide ion has a Kb of 1, and therefore it is a stronger base. So while we don't need to know these, the Ka or Kb values, we need to have an idea of the relative strengths of, some of the common acids and bases that we will be looking at. All right, so that leads us now to question 2, which is arrange the beta blockers and F-ortyl in the table from most to least acidic, right? So pause the video again and take a look at the Ka values. At this point, we are ignoring the error values, right? So we're just looking specifically at the pKa values seen here. All right, so if this is how you arranged it, then congratulations. So the key point that we're looking at, and let's just go back to this slide here, where we said the greater the pKa, the weaker the acid. So that should guide you in responding to that question. All right, so our follow-up question 2 says, discuss the statement, the stronger the acid, the weaker the conjugate base. So please have the answer to this question ready for our next class. All right, so now we're going to look at the effect of electronegativity. So the differences in electronegativity give rise to polarized bonds, right? Which, we already have an appreciation for. So in hydrogen fluoride, the differences in electronegative lead to, delta H and delta, delta positive H and delta negative F, right? So that means slightly positive and slightly negative. So this polarization suggests that the hydrogen atom is acid-like, right? So once there is deficiency in electron, it is acid-like, in that it's related to a proton. So bond polarization due to the presence of a more electronegative atom allows a more facile reaction with a base, right? So now we can see that a base can come in and pull our proton, that is delta positive, and breaks our hydrogen fluoride bond. So the R would start on the bond, ends on the fluoride, which is delta negative, and so we end up with the fluoride ion, which is our conjugate base, and our conjugate acid. All right, so now we're looking at the effect of atom size. So a bond between atoms that are close to the same size, that is hydrogen and fluoride, will have a shorter bond length when compared to the bond length between atoms of different sizes, naturally, right? So longer bond lengths between two atoms are associated with weaker bonds in chemical reactions, right? So the length of this bond, hydrogen iodide, is 161 pm, and the length of the hydrogen fluoride bond is 92 pm, right? So shorter bond, stronger bond. So the question here is, why is ammonia a stronger base than water? So as we saw previously, that water is amphoteric, so it's a weak acid and a weak base depending on the environment. So the question is, why is ammonia stronger than water? It looks somewhat similar. We have both of them have an electronegative atom in oxygen and nitrogen. One has 2 hydrogen, the other has 3 hydrogen. So structurally, if we look at it, they look similar. So why is it that one is a stronger base than the other? So the nitrogen atom of ammonia is a better electron donor. In other words, it's a stronger base than the oxygen of water, right? Than the oxygen atom of water. So the conjugate acid of ammonia is more stable. That is, this ammonium ion here is more stable and less reactive when compared to the conjugate acid formed from water. So our hydronium ion here. So let me repeat. The conjugate acid, which is the ammonium ion, this is more stable than the hydronium ion. Because it's more stable, it's less reactive. And so oxygen is more electronegative than nitrogen. So oxygen will retain electron density more efficiently than nitrogen. And so the oxygen is a weaker base relative to nitrogen. So another question here is, can we therefore predict the outcome of an acid-base reaction knowing all that we know? Can we predict the outcome? So acid-base reactions always favor the formation of the weaker acid and the weaker base. So the weaker acid or base are more stable, right? In other words, lower in potential energy than the stronger acid or base, right? So let's look at this equation here for a second. We have acetic acid with a pKa of 4.75. We have a very strong base here. And just to point out that this proton is transferred from the acid to the base. And based on that reaction, we have sodium acetate forming. So clearly the hydrogen is liberated, and this hydroxide ion abstracts our proton, and we end up with sodium acetate, and the pKa of water is 15.7, right? So the point here is that the acid-base reaction always favor the formation of the weaker acid and the weaker base. So in this case, the weaker acid is water, right? Is that right? The weaker acid is water. And so, when we compare our pKa values, 4.75 to 15.7, that is clearly the case. So consider the reaction between phenol and sodium hydroxide. Which acid-base reaction, if any, would take place? So I believe you should be familiar with this reaction as well. So we have our base in the form of sodium hydroxide. Again, it will abstract a proton as bases normally do. This OH bond will break and form the phenoxide ion. So we have sodium phenoxide here and water. Again, the reaction favors the formation of the weaker acid in the form of water. So we're comparing 9.9 here, pKa of 9.9 with a pKa of 15.7. Another important topic that we want to talk about is salt formation. Carboxylic acids with more than 5 carbons are insoluble in water but soluble in aqueous sodium hydroxide to form water-soluble salts. The solubility results from increased polarity, right? So the fact that we form ionic hydrophilic salt here, you increase the polarity. So just to mention also that it's a similar reaction when you think about when soap is made, right? We start off with a carboxylic acid and you react it with some base and you end up with a ion just like this, and it is now soluble in water, right? So very important point here that carboxylic acids, more than 5 carbons, insoluble in water, but once we once we make a salt, right, it now increases its polarity and therefore increases its solubility. So benzoic acid is insoluble in water. However, sodium benzoate is soluble in water. And sodium benzoate, I believe, should also ring a bell because it is used as a preservative in, your bag juice and other juices that you drink. All right, so similarly, so we can form a salt from amines as well. So amines, as we know, are bases and they will react with aqueous HCl. And so again, the aniline is insoluble in water, but once it is protonated by an acid, it now forms a water-soluble salt. So this is important for you, being PharmD students who will go on to do medicinal chemistry, in that drugs are often chemically made into their salt forms to enhance how the drug dissolves and to boost its absorption into your bloodstream. All right, so let's look at two, right? Cataflam versus Voltaren. And we have the backbone structure here. So diclofenac is a non-steroidal anti-inflammatory drug, and we just say NSAID for short. And it's used to relieve pain and inflammation, which I'm sure you know. Diclofenac exists in two forms. So the sodium salt is the diclofenac sodium, and the potassium salt is diclofenac potassium, right? So each has the same amount of diclofenac base. The main difference is that diclofenac potassium is slightly more soluble in water than diclofenac sodium. So the potassium version is slightly more soluble in water than the sodium version. So the diclofenac potassium is generally considered to be more quickly absorbed and have a faster onset of analgesic activity than the diclofenac sodium, right? I don't know what your experience has been, whether or not you have taken either, and if you have noticed any difference in terms of the speed of onset. So in terms of tying the brand name to the actual whether potassium or sodium, right? So Cataflam is the potassium and Voltaren is the sodium. So our third question here is, draw the structure of diclofenac and identify all functional groups. And part B says, suggest two positions on the molecule where you would expect to see an acid-base reaction. So pause and try to answer this question. All right, so if your answer was for the functional groups, right? So we have aromatic rings, right? We have our carboxylic acid in orange here. We have our secondary amine in blue. And we have our halide in green here, right? So another aromatic ring in red. All right, so for the acid-base reaction, we have a carboxylic acid here, which could react with a base, right? And we have our amine portion here, which could react with HCl. So for our follow-up question 3, it says, how does solubility of the salt affect activity? How does the solubility of the salt, and the salt we're referring to, any salt, but we can use the one, Voltaren or Cataflam. How does the solubility, if we compare both of them, affect the activity? All right, so another thing that we need to look at is how does hybridization affect acidity? And if we look at, when we compare our sp3 hybridized sp2, which is single bond, double bond, triple bond, sp3, sp2, and sp hybridized, the anion here, that is with the triple bond sp3, sp hybridized, sorry, is the most stable as compared to the sp3 hybridized anion. It is the least stable. And because of that, the alkyne is the strongest acid of all three because it is, the weakest base and therefore it's the most stable, right? As compared to the single bond, right? It is the weakest acid and we form this anion here, which is the least stable, or carbanion, and it is the least stable and the strongest base, right? So if we go back to what we were saying earlier, if it's the weakest base, then it's the most stable and the most potent acid. All right, so continuing our discussion, compounds containing nitrogen atoms with unshared electrons, for example, ammonia or other amines. So the nitrogen has one electron pair that can accept a proton, an ion, forming a plus charge, right? So we form an ammonium ion. So if we were to draw an arrow here, the arrow would start at the source of electron, which would be the nitrogen here, and it would end on the, where the electrons are going, forming a new bond here between the nitrogen and the hydrogen, and a plus charge would be generated on the nitrogen, which is an ammonium ion. All right, so let us consider compounds containing oxygen atoms. So what happens there? These reactions should be familiar. So we have our tertiary alcohol here in the presence of heat and an acid. This alcohol can be protonated by the acid. So the arrow starts at the source of the electron, ends on the hydrogen. This hydrogen chloride bond is broken, and as is evidenced by where the arrow starts and where it ends on the chlorine, right? So we end up with a chloride ion and we end up with this protonated alcohol, right? So because it's a tertiary cation will be formed. We can lose water. Water is a very good leaving group, sorry. So this bond can be broken, and the arrow starts here, it ends on the oxygen, which quenches the positive charge, and we end up with a tertiary carbocation, which is now susceptible to attack from the chloride, which was generated previously to form our halide seen here. So proton transfer reactions are often the first step in many reactions, and reactions that we looked at even last week of alcohols, ethers, aldehydes, ketones, esters, and carboxylic acids. So what about our double bonds, right? When we see, even last week we saw some reactions where the arrow started on the double bond and it ended on the, the electrophile, in this case the hydrogen of the hydrogen chloride in the presence of ether, we form a carbocation. So once this one of these bonds is broken, the new bond is between this carbon and the hydrogen, and therefore a carbocation is now on this carbon here, right? And another double bond is that of formaldehyde. So the arrow starts here and it ends on the hydrogen again, and the hydrogen chloride bond is broken and we form the chloride ion again in the presence of ether. So we form an oxocarbenium ion. So the reaction between HCl and ethene, which is here, involves donating 2 electrons from the alkene, as we saw, right, to the acidic proton of HCl. So both ethene and formaldehyde react as weak Bronsted-Lowry bases with the strong acid HCl to yield their conjugate acids seen there. So yes, they're also acid-base reactions. All right, so this is another example of the basicity of an alkene, right? This alkene is cyclopentene. So if we tried to react cyclopentene with an alcohol, there would be no reaction. If we put in water, no reaction. And if we tried various other substrates, there'd be no reaction. However, similarly, as we saw on the previous slide, that if we reacted with HCl, it will be addition reaction to form a carbocation. And as we also saw, once in this case, a secondary carbocation is generated, the chloride that is liberated at this step can now attack our carbocation to form our chlorocyclopentane. So are carbonyl compounds acids or bases? Well, let's look at it. So we have butanol, right, which is an aldehyde. And so both, whether aldehyde or ketone here, reacting with HCl and boron trifluoride. And, for the HCl, the carbonyl oxygen is protonated. So when an aldehyde or ketone reacts with a Bronsted-Lowry acid, the conjugate acid that is formed is a protonated carbonyl and oxycarbenium and ion as well, right? So here we have a protonated carbonyl being formed, and you would have seen that previously. All right, so at this point you might be wondering, what is the biological relevance, apart from the drugs, within our system, what is the biological relevance of acids and bases? Well, if we look at two conditions, acidosis and alkalosis, the acid-base equilibrium process of metabolic acidosis and metabolic alkalosis. So the body can generate acidic compounds that can change this pH. So making blood or tissue more acidic as a result of the natural breakdown of fats, right? So bicarbonate can be generated to react as a base, right? And for respiratory acidosis, it occurs when breathing abnormalities result in carbon dioxide retention from inadequate ventilation during anesthesia or drug use. And metabolic acidosis occurs with starvation, uncontrolled diabetes mellitus, with ketosis, and electrolyte and water loss due to diarrhea. So if we look at this table here, which breaks down the differences between the acidosis and the alkalosis, for the respiratory acidosis and alkalosis, right? So we have normal bicarbonate ions here. For the acidosis, we have increase of carbon dioxide, and for the alkalosis, we have decrease in carbon dioxide. And clearly, if it's acidosis, we have a decrease in pH, and if it's alkalosis, we have an increase in pH. as a result of an increase in the carbon dioxide. For metabolic acidosis and metabolic alkalosis, right, the carbon dioxide concentration is normal. However, the bicarbonate concentration is what decreases with acidosis, and the for alkalosis, the bicarbonate concentration increases. And as we saw previously with the respiratory acidosis and alkalosis, similarly, for acidosis, accompanied by decrease in pH, right, and alkalosis, increase in pH. So I mentioned these two previously. However, just to say that the respiratory alkalosis results from hyperventilation, which produces lowered CO2 partial pressure and the higher pH of extracellular fluid. While for metabolic alkalosis, it can result in the loss of gastric juices that are rich in HCl and from excessive sodium bicarbonate ingestion, and it is associated with potassium ion deficiency. All right, so just a table which compares both acidosis and alkalosis. So acidosis is a condition of having a lower pH than the normal pH of the blood. So once the pH is lower than 7.4, you have acidosis, while alkalosis is a condition of having a higher pH than the normal pH of the blood. So greater than 7.4, and we have alkalosis. Academia is caused by acidosis, and alkalemia is caused by alkalosis. And as we mentioned before, for acidosis, the pH of the blood is below 7.35. The pH of the blood is above 7.45 for alkalosis. Metabolic acidosis and respiratory acidosis are the major types, while metabolic alkalosis and respiratory alkalosis are the major types for the alkalosis. And just to add to the biological relevance, the cell membranes are structures containing lipids and proteins as their main components. So many drug molecules are weak acids or bases and can therefore exist as ionized species, which you will see, particularly when you do medicinal chemistry in the future. Depending on their pKa values, and that is why we need to have an understanding of pKa and the pH of the environment. So one of the more important concepts related to drug absorption is that ionized species have very low lipid solubility, right? And that should make sense, and are unable to permeate through membranes, right? So that is very, very important knowledge to have. And only the non-ionized drug is usually able to cross membranes. So just to look at, lidocaine HCl, and that is the structure of the compound. So many local anesthetics block nerve conduction by reducing membrane permeability of sodium ions. So lidocaine specifically is usually distributed as an aqueous solution of the HCl salt. And by this point, we should understand this statement, which is the conjugate acid of the reaction of lidocaine with HCl. At physiological pH, which is approximately 7.4, most of the drug will exist in its ionized, which combines with the excitable membrane to inhibit sodium permeability, right? So the point we're making here is that when you consider, these drugs, It's very important, which form it is in, whether or not it can cross, the lipid membranes, or, it will just stay in blood plasma. All right, so now we're going to go to the other part of the lecture, which is reaction mechanisms. So just an introduction. So in many reactions, starting materials are converted directly into products, as we have seen. In organic reaction mechanism, it's a step-by-step description of the movement of electrons and bond making and bond breaking processes. It is an understanding of the nature of any intermediate that may be part of the process, right? So as we have seen, throughout our chemistry life, and obviously when we're talking about reaction mechanisms, we're talking about arrow movement, right? And as I have stressed previously, it tells a story of what is happening step by step, where are the electrons going, and it gives us insight into the intermediates that may be produced along the way. So that takes us to thermodynamics, which is, we have to have some amount of understanding of thermodynamics in order to fully understand reaction mechanisms and organic chemistry by extension. So chemical reactions are driven by changes in energy, right? So we know about free energy, the energy of the entire system. The free energy is a function of the enthalpy, right? So if we recall, enthalpy, the hydrogen, entropy, which is the S, and T, which is temperature, right? So let me repeat that. The energy of the entire system, the free energy, is a function of enthalpy, entropy, and temperature. So whether or not a chemical reaction will proceed spontaneously is determined by the change in the standard free energy, which is delta G, right? So for most reactions in organic chemistry, entropy is small. So this value here is small for most reactions. So we will assume in most, if not all instances, that this value is a very small value. So if the entropy term is assumed to be 0, then the change in free energy is equal to the change in enthalpy, right? So if we're saying, if the entropy is 0 or close to 0, right? If we have 0, we multiply it by T, then all that's left is delta G equal to delta H. That's what we're saying here. And we're going to assume that for most reactions in organic chemistry. So as you would have known, if the free energy, the change in free energy is negative, if it's a negative value, energy is released during the reaction, and this reaction is an exothermic process, and the reaction is said to be spontaneous. Conversely, if delta G is positive, the process is endothermic and the energy must be put into the system for it to continue. If one reaction has a negative delta G or free energy, change in free energy, and a second reaction has a positive change in free energy, the first reaction is assumed to be faster and easier. However, no reaction can occur until energy equal to the activation energy is attained, right? So in a little bit, we're going to look at some energy profile diagrams, right? So we need to have certain amount of activation energy for any reaction to happen. So for competing reaction pathways or reversible reactions, previously, we saw some reversible reactions. If one reaction is more exothermic than the other, it is assumed that the more exothermic reaction will lead to the major product. All right, so everything comes down to thermodynamics. So let's look at bond dissociation energy. So let's look at this reaction with sodium iodide and methyl chloride, right? So in this reaction, we have a CCl bond. It's broken, right? So the arrow starts here. So that means that the iodide is being nucleophilic. It attacks our carbon here. And this CCl bond is broken, as is evidenced by the arrow starting here and ending on the chloride ion. So we end up with sodium chloride and iodomethane. So in this reaction, the CCl bond is broken, right? This bond here, in chloromethane, right? And a new Ci bond is formed in iodomethane. So the bond energy for CCl bond in chloromethane is 351.5 kilojoules per mole, and the bond energy for the carbon anion bond in iodomethane is 234.3 kilojoules per mole. So if we calculate the change in enthalpy, the change in the product minus the change in the enthalpy of the reactants, if you do that calculation, you can tell me if you get a negative value, right? So if we recall this reaction here, and if we're saying that the entropy is small or zero, then whatever we work out to be the change in enthalpy, it would be equal to the delta G, or the change in free energy. So just to look at transition states for a second. By the way, I expect you to, do the subtraction. Tell me if you get a positive or negative value, and, and therefore tell me if this reaction is spontaneous. So the transition states is another thing that we need to know when we look at these energy profile diagrams. When we react A plus B, we have a transition state, and that gives us, a new bond, right? And so this transition state, right? And what it really means is that, the bond isn't fully formed or fully broken yet. That's really what the transition state is. It is in between the bond forming and the bond breaking. So it's that in between, right? So it hasn't fully formed yet. In this case, this particular bond hasn't fully formed, and when you get the product is when it is fully formed. The transition state therefore cannot be isolated or observed, right? So it's just humans postulating that, okay, there must be a stage that happens between, in this case, the bond forming, when it's almost formed. So note all elements of this energy profile diagram, including delta G, right? So we have the change in energy on the y-axis. We have the reaction coordinates on the x-axis, right? We have our starting material here, and we have our product here. And the difference in delta G between the starting material and the product is here. So whether or not that is negative or positive will tell us, is it endothermic, is it exothermic, or is it spontaneous or non-spontaneous? And we mentioned the activation energy, right? We need to have certain amount of energy in order for any reaction to happen. And our transition state is this state here, where we're saying the bond hasn't fully formed or broken, in this case formed, right? So that is considered to be our transition state. So we must know how to draw an energy profile diagram, labeled axes and all of the elements. So that leads us now to question 4, which says draw a fully labeled energy profile diagram. That's A. And B says identify it as exothermic or endothermic reaction, as an exothermic or endothermic reaction. So pause here. All right, so whether or not you chose to draw an exothermic or endothermic reaction, it should look something like this. So our exothermic reaction is, one similar to what we saw earlier, where we have our reactants up here and we have our products at a lower energy, right? So this is the energy that is released, and that is why it's a exothermic reaction, or axes are labeled. And for the endothermic reaction, if you chose to draw that, your products will be of higher energy than your reactants, and energy needs to be absorbed for this reaction to happen. All right, so our follow-up question 4 says explain the diagram. So you're looking at this diagram and you're going to talk me through it. You're going to tell me, what is it saying based on our thermochemistry. All right, so let's just go into our energy profile diagram a little bit more, because we're going to look at it for, various types of reactions, right? So here on the y-axis, again, we have our energy. On the x, we have our reaction coordinates. We have our reactants here. We have our activation energy. This is our transition state. In this particular reaction, clearly our product is the iodomethane, right? So this bond is being formed and this bond is being broken, right? So that is our transition state. The bond isn't fully formed or broken at the transition state. However, once it crosses that, activation energy, we form the product. So we have a fully formed product in the form of iodomethane here. All right, so what if the reaction has more than one step? So which step controls the rate of the reaction? In principle, reaction intermediates may be isolated. So notice that there's a difference between a reaction intermediate and the transition state, right? You must be able to distinguish between both. So they have a definite lifetime, which may be long or short. These are the intermediates. Remember, we said we cannot isolate a transition state, but we may or may not isolate an intermediate. So here, if the reaction has more than one step, we have an intermediate here, right? So it would have crossed the transition state, form an intermediate, and have another transition state, and then form the product here, right? So if the reaction was stopped at an appropriate time, the ammonium salt could be isolated. So here we have an excess of the halide here reacting with the amine, and we have our ammonium salt, right? So the The point we're making here is that if the reaction was stopped at an appropriate time, the ammonium salt could be isolated as an intermediate. So just some points to remember. The products with a lower energy are said to be more stable, right? So if we look at our energy diagram, the lower in energy, the more stable. More stable than those with high energy. Lower energy correlates with greater stability and poorer reactivity. So in terms of the change in free energy, a lower energy product formed via an exotherm reaction will have a larger delta G than a product with a higher energy. If the delta G is larger, the lower energy product is more stable. Transition states cannot be isolated or observed, as we said before. It is possible to isolate or observe an intermediate depending on the reaction, but not a transition state. The transition states are assumed to be the logical midpoint of a reaction, but they cannot be observed, as I said before. All right, so these are some examples of reaction profiles. So for our SN2 reaction mechanism, which we have met several times, we have our starting material, which is our halide and our hydroxide ion being nucleophilic. So we know our mechanism already. And this is our transition state where this bond is being formed and this bond is being broken. Once the bond is formed and the bond is broken, we have our products here. So how does the reaction profile look? This is how the reaction profile looks for the SN2 reaction. So the energy of the transition state determines how fast the reaction will proceed. The higher the transition state energy, the slower the reaction, which should make sense. All right, so let's compare that to the SN1 reaction mechanism. So for the SN1 reaction mechanism, we have our starting material here. So we have a tertiary alkyl halide. So therefore, this bond can be broken, right? And then this is our first transition state where this carbon iodine bond is almost broken, right? And then it forms our carbocation intermediate. So just in case you were wondering, give me an example of an intermediate. This is an example. We have a carbocation, which is an intermediate. Now we have a nucleophile here in the form of cyanitrile, and it will attack our carbocation to form a second transition state. So notice that with our SN2, we only had one transition state compared to our SN1, in which we have two transition states and then our substituted product. So that is very important for us to know. All right, so the carbocation is a short-lived species, right? That's why it's an intermediate, which is formed en route to the products. Intermediates have a finite lifetime. Carbocations are planar and stable. Attack from either face leads to racemization, right? So in this case, it could attack here or it could attack here, right? And because both attack happens, you get racemization, as opposed to the SN2, where you just have one, backside attack. All right, so let's consider this reaction. So we have, the same reaction that we saw previously where we have, an alkyl halide. And we're going to just talk through the energy profile diagram. All right, so our first step, which, so these are similar steps to what we saw just now, right? So we have a alkyl halide. So this carbon chlorine bond breaks to form our carbocation here and our chloride ion, right? So this is our step one, and therefore we have the activation energy and we have the first step, right? So that is this part. So the blue section, if you follow the blue square, or not square, rectangle here, they correlate to the different steps, right? So step one is this blue rectangle, step two is this one, and step three is here, right? And so our transition state also varies. So for this transition state here, right, or carbon chloride bond is being broken, right? So that's the first step. For the second step, and then we have formation of the intermediate, which is the carbocation. So this sink here would be the formation of the carbocation. So our first intermediate or first transition state. Our carbocation intermediate now undergoes an attack from water, all right? And once that happens, we form another intermediate, right? So here would have been our carbocation, and our transition state here would be the formation of this carbon oxygen bond. So this bond is not fully formed in the transition state here. So this is our transition state for the formation of our oxygen carbon bond, right? So so that is this part here. So after we form this intermediate, right, we have to lose this proton here to form our alcohol. And so the water will abstract the hydrogen, breaking this oxygen hydrogen bond to form our alcohol. So this is our third step and our third transition state. So this transition state involves the breaking of this oxygen hydrogen bond, right? So that is here. And then formation of our product, which is our alcohol here. Tert butyl alcohol and hydronium ion are our products here. So I hope you are able to follow through the steps. It's kind of going into more detail than we saw in the previous slide. All right, so what about our elimination reaction on the energy profile diagrams? Are they similar to the substitution ones? Well, let's see. So this is E2 reaction profile, and we have a reaction here. And does it look similar to SN2? Yes or no? So in the transition state, the carbon hydrogen bond and the carbon bromine bonds are partially broken. So the OH and the pi bonds are partially formed, and both the base and the departing leaving group bear a partial negative charge. So here, so let's back up a bit. So we're looking at this reaction, right? It's an elimination reaction. And perhaps, we should draw this one out just a little bit for clarity. All right, so we have the carbon, and it's bonded to 3 carbons. Let me just draw the third one, all right? And it's bonded to a bromine, right? So the idea here is that we have an elimination reaction, right? So in the presence of the base will abstract a proton, and then we form the double bond, and then the bromine leaves, right? So a lot of things are happening here. So this carbon hydrogen bond is being broken, this carbon carbon bond is being formed, this carbon bromine bond is being broken as well, right? So this is the transition state, right? So this is the same thing, as what we have up here. Just showing that, this bond is being broken, this bond is being formed, this bond is being broken, this one is being formed, right? So that is the transition state. Not as simple as our SN2, but nevertheless, it is just one peak, right? And then after the transition state, we form a or alkene, right? Or carbon carbon double bond formed here. Okay? All right. So for E1 reaction profile, that looks different, doesn't it? So here we have our alkyl halide again. We have our first transition state, or step 1, and then we have our intermediate here. So this one should be familiar to or similar to our SN1, right? In which we have a carbocation intermediate here, and then that leads us now to our second transition state, and then we have our products in the form of alkene and hydronium ion and or iodide, right? So again, for E1, similar to our SN1, in which we have a carbocation intermediate. So we have an image here of our carbocation intermediate. So clearly we have our halide bond being broken here to form our carbocation, and then we have loss of our hydrogen and that is our second transition state to form our alkene here. Any questions, guys? Just remember to make note of your questions. All right. All right. So here we're looking at the addition reaction profile, right? So in this case, we're not forming a double bond. In this case, we are adding to the double bond, right? So you should be familiar with, the word or the person, Markovnikov, right? So we have our Markovnikov product on this side, and we have our anti-Markovnikov product here, right? So we have a double bond, and we're adding to this, adding HCl to the double bond. So for our Markovnikov product, we have the carbocation intermediate here, right? For anti-Markovnikov product, we have the plus charge here. So the plus charge is here for the Markovnikov product, and the plus charge is on this carbon for the anti-Markovnikov product. So that is those are our two intermediates. Please notice that notice the energy difference. So this is higher in energy than this one, right? This is lower in energy, which means it's more stable. And then after that, we have another transition state. So we'd have one transition state to our carbocation intermediate, and then we have attack, right? So we have attack of the chloride ion to the carbocation, and that's a new bond. And so that's why we have a transition state here when that CCl bond is being formed to form our Markovnikov product, which is also lower in energy. right? So for anti-Markovnikov product, a similar reaction happens where you have the chloride ion attacking our positive center or carbocation, and then we have our second transition state, which is clearly, when you have the carbon chlorine bond almost being formed or partially formed, and then you form the anti-Markovnikov product seen here, right? So similar energy profile diagrams. All right, so the final thing that we're looking at for today's lecture is a comparison of addition to alkenes and alkynes, right? So addition again, but we're adding to an alkene here and we're adding to an alkyne here, right? So we're adding HX, as you know, represents some halide, right? And so if we're adding, a first transition state would be breaking off one of these bonds, right? And so we form a carbocation intermediate, as is represented here. So or hydrogen. So if we just imagine this bond being broken, right, on the hydrogen, so a new bond is formed between one of the carbons and hydrogen, and we have formation of our anion here, right? So we have our carbocation and our counter ion, and that is our intermediate. All right, so for our second transition state, we have formation of our a new carbon X or halide bond, right? So the halide would attack the positive center to form a new bond here. So let's compare that with the alkyne, right? So a similar first step, a breaking of one of the triple bonds to add hydrogen to one of the carbon, and a carbocation is generated on the other carbon, as we see here. So we also have a intermediate, and then our second transition state would be the addition of our halide anion to our carbocation center to form our alkene product here, right? So we have our vinyl carbocation intermediate, and it is, if we look at the relative energy, it's higher in energy than our saturated carbocation, right? So that obviously means that this is more stable than the vinyl carbocation seen here. All right, so that leads us to our final question. Question 5, and it is, why is the Markovnikov product lower in energy? So just go ahead and pause the video and answer the question. All right, so if you answer, the Markovnikov product is lower in energy because it is a product formed via the more stable or lower energy carbocation intermediate, then you have gotten the correct answer. Congratulations. So our final follow-up question 5 is, propose 2 mechanisms, and I already talked you through it. So all you have to do is to just draw the arrows, right? Propose 2 mechanisms for the 2 reactions shown below. All right, so please attempt it at least. All right, so that's where we end. Thanks so much for watching. Remember to make all your notes and answer the questions so that we can have a robust discussion when we meet.